Hello and welcome, and this is the video for Lab 8, and this is for Group 5 for Holton, Tim, and Nick. So I'm going to give you a brief introduction here. So Lab 8, we performed a drop test on the landing gear, and you can see it here in Figure 1, what the landing gear looks like. So you have a wheel here, and then you just have two beams connected to this little box here, and that's connected to this larger beam that's demonstrated by these dotted lines here. So you can see we're going to be studying the behavior of this landing gear as it's dropped from a couple different heights. So we're going to look at the reaction of both the angle right here and just the acceleration of the whole thing. So that you can see the second bullet point, we're going to be studying the acceleration and the stroke, which is derived from the change in this angle here, through an accelerometer, which is going to be up here, and that's just sensing the acceleration of the landing gear, and a potentiometer, which is here, which is sensing, that's just an angle sensor. And then we've also got this photodiode, which you can see down here at the bottom of Figure 1. So we have a laser pointer pointing at the photodiode before the landing gear is dropped, and then as the landing gear is dropped, it's going to drop down and trip the laser pointer. And so we're going to use a method where we're not taking data until that is tripped, and so that way we don't have to take data over long periods of time. Now I'm going to hand it off to Tim for the procedure.
Okay, so here are the procedures. So first we talk about the instrumentation. So right here on the right, we have the landing gear model that we used with all the dimensions as well. We also have the piezoelectric accelerometer attached to the landing gear, which is better seen in this previous figure here. We have the rotary potentiometer, which measures the angle right here. And we have the photodiode and laser pointer, again, shown here. And you have the LabVIEW data acquisition software. So as for the LabVIEW setup, you have the data acquisition assistant, which gathers data, and it's actually being stopped by this trigger and gate. And then it collects data collector, and then it writes the measurement and makes waveform graphs. So the big thing here that's different is a trigger and gate. So this prevents the collector from measuring data and showing data until after the photodiode is triggered. And the specific trip we sent it was to 1 volt. So if there's an amplitude change of at least 1 volt, the gate will open and the collector will start running data to the measurements. Experiment setup. So we used an accelerometer, a potentiometer, and a photodiode, which is all supplied by 5 volts of power. The piezoelectric accelerometer was used in experiments before, same with the potentiometer, so we use the same setups as before. And then for the photodiode, this is the configuration on the right that we used with a noise filter and the photodiode located here. Data collection. So how we ran the experiment was we had 3 trials for each person, dropping at 3 different heights, which was 37.8, 45.7, and 58.2 centimeters. And that's the distance from the bottom of the wheel to the table, which was how far the whole landing gear setup fell to the ground, like the distance it fell. And before the experiment was ran, we made sure the laser pointer was pointed to the photodiode, so that when this whole thing fell, it would properly trip the photodiode, and the gate would open in LabVIEW and start collecting data. And after the sensor was tripped, it measured data for 5 seconds at 1 kilohertz, so 5,000 samples. Data interpretation. So after we got the readings from the voltage of the potentiometer, we used this graph here on the right to correlate the change in output voltage to the change in angle. So we assumed the initial angle was 0, so theta, which is our final angle, is equal to the voltage change times 90 degrees over 4 volts because that's like the linear correlation here. And then after that, we took the change in angle and we used some simple trick to find the stroke length or the change in stroke length h. And you got h equal to 15.45 centimeters times sine theta of the angle here. And yeah, this is the this image here shows the stroke length, and it is the vertical displacement of the wheel. So that's why we use the hypotenuse of the triangle here, 6 inches converted to centimeters. And then finally, this is our data interpretation for the piezoelectric accelerometer, which again was used in labs before. And this equation here is V is measured voltage, C is the calibration constant, and A is acceleration in meters per second squared. And the acceleration constant C was 0.01 volts per meters per second squared. And yeah, you just do a little division and it gives you acceleration in meters per second squared.
So I will be presenting my results, and then I will be talking about improvements that could be made to the lab. So first up, we have acceleration data. This came from 3 runs. One was done at 37.8 centimeters, which is the one in blue. The next drop was done at 45.7 centimeters in red and 58.2 centimeters in green. These acceleration readings come from a piezoelectric accelerometer, and these are happening when the landing gear impacts the table, and the sensor is getting all this these massive magnitudes of acceleration. So the data does not reflect what you would expect. We can see that the lowest magnitude is at the lowest drop height, but the greatest magnitude is at the middle drop height. And we believe this happened because of issues that we have with our sensors shifting around when the test rig would impact the table. The other data sets showed what you would expect normally, where the highest magnitude was at the largest drop height, the lowest magnitude was at the shortest drop height. In this case, you still can kind of see the trend, except for this massive magnitude from 45.7 centimeters, clocking in right about negative 700 meters per second. Moving on to stroke length. This was defined as the change in height of the trigger point, which was where the strut for the landing gear of our test rig meets the spring and damper assembly. Now, this was calculated from an angle sensor reading of angle, and we used this reading to calculate how the point was shifting as the rig was impacting the table. And we can see that the data is a little bit messed up because of the issues that we have with our sensors, but we can still gather some sort of conclusion from this. Even though the stroke length shows a very large jump after the spring and damper assembly have settled, we can see that the largest magnitude or the largest length for stroke length happened at the highest drop height of 58.2 centimeters. We can see how this is going along 0 and then spikes up on impact, reaching the highest value when the damper is fully compressed. And as the damper expands, this goes back down to its 0, or what should have been 0 without the issues that we had. Again, the faulty test setup is to blame for this massive jump here at 37.8 centimeters. The jumps were smaller here at 47.5 or 45.7 and 58.2 centimeters. But we can still gather the general trend from this plot.
Okay, so these are my results. So first, the acceleration. So you can see clearly that as the drop height increases from 37.8 to 45.7 to 58.2, according to these colors, the maximum magnitude of deceleration actually it faces is increasing with drop height. So first for 37.8, it's at around 500-ish meters per second squared. For the red 45.7, it's around negative 700 meters per second squared. And then for the green 58.2 drop, it's around negative 800 meters per second squared. It's an expected pattern that we want to see. And the reason why the magnitude is so large is because the deceleration it experiences is within like 1,000th or 2,000th of a second. So the amount of acceleration needs to go from free fall velocity to zero velocity when it's resting on the table is expected to be a large form of magnitude. And yeah, these patterns are what we expect to see. As far as stroke length goes, as the stroke length drop height increases, the magnitude of the stroke length change due to the force of the table increases as well. So that means the stroke length also increases because the spring will need to, compress more to decelerate the to absorb the impact of the table. So for 37.8 centimeters, the maximum stroke length displacement is around 0.2 centimeters. For 45.7, it's around 0.25. And then for 58.2 centimeters, around 0.4 centimeter stroke length change. Again, this is expected. And again, we're only looking at the peaks here because that is where the initial force, if you go back to the acceleration graph, that is where these forces are experienced. The maximum acceleration is where these peaks of the stroke length are. So that's what we're really interested in. And then the errors that we can attribute to some of these, not the noise, but the reason why the stroke length is so little is because the grip friction tape between the joint and the angle potentiometer is worn down over time due to many trials and our group being later in the week. So the angle potentiometer was less responsive. And yeah, this is part of the reason why some of the changes, like from 45.7 to 37.8, the difference of stroke length is so little.
So here I'm going to talk about my results a little bit. Of course, they were very similar to Tim and Nick's, so a lot of the same conclusions here. But here's my acceleration data. We see this is an impulse response, which would be expected because as we're dropping the landing gear, it's very quickly falling, and then it's going to go right back to zero as soon as it hits the ground. But so we see these big spikes in each data set here, which is an impulse response. And then it's just zeroing right back, which is, you can see it here in the green, that's when it hits the ground, and then the same thing over here with a little bit of noise, but that's to be expected. There is a bit of an oddity here in my data compared to Tim and Nick's, in that the drop at the red and the blue levels for the 37.8 centimeters and 45.7 centimeters, those are showing about the same magnitude in the spike here, which is not expected. We would want to see this red spike larger than the blue, which is what we see in Tim and Nick's data. So I believe this is just an error in either our data collection or there was some fault in the sensor or something like that to explain this. And we're going to say the same thing here in the stroke length. For some reason, this is also the same magnitude, which is not what we would expect. We would expect the red magnitude to be a little larger. But again, that would be to the same error that occurred in the acceleration data. But here in the stroke length, we see the same kind of trends, that there's a large spike here in the yellow, and that's the largest drop, which is what we would expect. Another kind of odd thing that we wouldn't expect in this data is that it's not, all these graphs are not zeroing to the same place. But we believe that that's due to, we had on our landing gear, there was some tape that was a bit just worn down from being experimented on so much. So if we were to do this again, we would probably fix that tape up and try and get some better data. But we would expect these all to go right back to zero when they're finished, or at least go to the same point. It's odd that they're all going to different points. But yep, that's about it. And then I'm going to talk about the conclusions here. So conclusions. So yeah, as we expected, we found that the magnitude and the acceleration of the stroke length increased as the landing gear was dropped from increasing heights. We didn't see that in my data, but in Tim and Nick's data, it was shown pretty clearly that as the height was increased, these magnitudes kept going up. And then, as we talked about, there's some inconsistencies, but we thought that was due to our experimental setup. There was just some problems with wear and tear, and the spring could have been better than it was. And we would want to fix that if we were to do the experiment again. But yeah, so we saw these inconsistencies in the stroke length. It's just, potentiometer shifting, and is fixable things that we would want to fix up next time we do the experiment.
Some improvements that could have been done to the lab. First and foremost, we would have fixed the issues that we had with our sensors. I think that was the most confusing part for us as far as analyzing our data and looking at our results. Luckily, we had several sets of data that we could cross-reference with and realize that some sets were had more error than others regarding the sensors moving around, especially with this one. This one was probably our worst. Again, reflected in the acceleration. Another interesting improvement would be to add more heights. I would say about 5 heights, maybe even more, just to get more data points and compare. I think that was a saving grace for us, that we had about 9, three heights for 3 group members, so about 9 data sets. And luckily, the error did not propagate to all data sets, so we were still able to gather a clear conclusion of what was going on to the lab. For sources of error, I think we could do better with noise in instrumentation, especially with this angle sensor. We can see that the magnitude of noise is relatively high compared to the accelerometer. The accelerometer, of course, the magnitudes felt when hitting the table were so high that they dwarf everything else. But with the angle sensor, we can definitely see some serious oscillation going here from noise. Another improvement that we could make to error would be to having some sort of mechanism to drop from the same height. Having us drop the rig by hand introduces human error and can cause variations in the height at which it was dropped. So when I think I'm dropping it at 58.2 centimeters, maybe I'm dropping it at 59 centimeters or 57 centimeters. And this could definitely cause some issues in our readings and expected results. Thank you.